So we're going to talk about rank and nullity for way too long here. There are a lot of questions for this one. And the main topic, or the main equation that we'll need for all of these questions is that the rank of a matrix plus the nullity of a matrix is equal to the number of columns of that matrix. Nullity being the dimension of the null space, and rank being the number of pivots or the dimension of the column space. So let's apply that to number one here. So we have a matrix A, and we're looking for all the values of C for which the system AX equals 0 has a non-trivial solution. So let's try to reduce this down. Sometimes things get pretty hairy when we have these unknown terms in multiple rows and columns at the same time. So hopefully things don't go too wrong. So just before we start though, what are we looking for? So AX equals 0, that's the set of all solutions to AX equals 0, so our null space. If that is a non-trivial solution, that means that the dimension of our null space is greater than 0, which will only occur if we have fewer than 3 pivot positions. And well, in order for us to have fewer than 3 pivot positions, we'd like to be able to add a row to another row, or subtract a row from another row, and get an entire row of zeros. And right here, what if this C is a -1? If we have -1, -1, we can add row 1 to row 2 and get a row of zeros. So -1 is clearly one of our answer choices. That said, we can't really see anything else from here. So let's see what we can do. Let's subtract row 1 from row 3. That gives us a 0, a -2, and a C minus 2. Let's subtract row 1 from row 2. +1, 0. And you can see that at this point we could have just solved for that C is equal to -1. But let's see, how can we get rid of this issue right here? Let's add 2 row 2's to row 3. That'll give us 2C there and C minus 2. So there's no value of C that will make that 0. Interesting. That said, what if C is equal to, no, 2 doesn't work. What about 1? Okay. This sometimes happens, and this is what I was kind of talking about, where when we have this unknown term in a different column and a different row, things can get a little weird because it's kind of impossible to, definitely not impossible. I'm definitely making a mistake here. I'm just not exactly sure. I'm not exactly sure what it is. So what we're going to do, which you can always do for these problems, is just plug in the other potential answer choices. So I think there may have been some mistake I even made along the way. So we're going to get rid of this and just write 1, -1, 2, 1, C2, 1, -3C, and plug in -2, 1, and 2 and see what we get. -2 and -2. Let's see if that works for anything. Let's subtract row 1 from row 2. Let's subtract 3 row 2's from row 3. And let's subtract row 1 from row 3. -4. We can turn that into a 1. We can turn this into a 1. Oh, there are 3 pivot positions right there. So A is definitely not correct. What about plugging in +1? 1, -1, 2, 1, 1, 2, 1, -3, 1, -3, 1. So yeah, we're plugging in there. What about this? Let's subtract row 1 from row 2. We get 0, 2, 0, we can turn this into a 1 and use it to set this term and this term to 0. And then if we subtract row 1 from row 3, use that to set that to 0. Oh, so nope, that's no good. That also reduces down to a you know what I mean, thing, matrix, identity matrix. And let's plug in our final answer choice, which would be plugging in c is equal to 2. 1, negative 1, 2, 1, 2, 2, 1, negative 3, 2. What can we do here? Let's subtract row 1 from row 2, 0, 3, 0, and subtract row 1 from row 3. That gives us 0, negative 2, 0. And we can use row 2 to set row 3 to 0. And there we have it. So let's see, up here, could we have figured out that our other potential answer was true? Was 2, sorry, assuming that we've done all of the correct work up to this point. Well, if we plug in 2, we will have a 3 here, a 4 here, and a 0 here. Yeah, so we totally could have figured that out. But you'll see, it's very much not obvious. Just a little annoying. I probably could have made this easier for myself in some way, but worst comes to worst, with these problems, always plug in your answer choices. So E is our correct answer. 12, let's determine the rank of this matrix. That just means row reducing it and seeing how many pivots we get. 1, 4, negative 1, negative 1, 7, negative 10, 3, 2, 7, 2, 1, 5. Let's see. Make sure I wrote all of those correctly. Okay, we're good. Let's subtract 4 row 1s from row 2. That gives us 0, 11. We're subtracting 12 here, right? Minus 12. So negative 10. And we're subtracting 8 here, so negative 7. Now what? Let's add row 1 to row 3. We get 0, negative 11, 10, and 7. Look at that. We can multiply this row by negative 1, or however you want to do it, but we can use row 2 to make row 3 a row of zeros. And we see we have 1 pivot position, 2 pivot positions, so our rank is 2. Assume that a 4x4 matrix A is row equivalent to this thing here. Which of the following statements is true? Okay, so is B in row reduced echelon form? Well, we see a stair-step pattern of pivot positions, which is awesome, and we see that every position above a pivot position is 0, so that's good. And then finally, all of our pivot positions are reduced to 1s. So yeah, no, we're in reduced echelon form, so this is false. The determinant of A is not equal to 0. Well, if we multiply the main diagonal of this matrix, we'll get its determinant. Because it's an upper triangular matrix, all of these positions down here are equal to 0. And so our determinant is 0, so this is not true. What about C? The null space of A has dimension 3. So if we see, counting our pivots, we see we have 3 pivot positions, so a rank of 3 plus our nullity is equal to the number of columns, which is 4. So our nullity is 1, so the dimension of the null space is 1, not 3. Now the column space of A will have dimension equal to the number of pivot positions. So our dimension of our column space is 3 and not 2. And so hopefully E is correct. If AX equals B is consistent for some B not equal to 0, then it has infinitely many solutions. Well, let's just think about this graphically. We are going from 4 dimensions to 4 dimensions, but you'll see that we're only really outputting in 3 dimensions out of those 4. So we can kind of bring this down into a 3D example. Let's say we had a matrix. This is an example that I use a lot. This matrix right here moves the first basis vector in R3 to where it started at 1, 0, 0. The second one to 0, 1, 0, which is where it started. But it takes the basis vector on the z-axis that used to be, right there, and moves it to the origin. And so as a result, all non-zero z vectors are squished onto the xy plane. And so this is similar, but it's harder to conceptualize because it's four-dimensional. But it has the same principle where because we have a matrix with control over fewer dimensions than the input space that it started with, it's going to be squishing infinitely many solutions onto every single individual point of the output space. So in this example right here, let's say if we're looking at the xy, no, I'll actually draw it in 3D. If we have our 3x, y, z here, this point right here, this vector, has infinitely many solutions that lead to that vector when you apply the transformation, and those are all of the vectors when you go infinitely up in z and infinitely down in z, because all of those will be crushed onto the same point. So E is correct. Question 15, let's find the nullity of this matrix. So let's rewrite it and start row reducing. 1, negative 2, 0, 3, negative 4, 3, 2, 8, 1, 4, negative 1, 2, 0, 4, negative 3, and 1, 5, 7, 6, 0. Okay, let's add row 1 to row 3. That will give us a 0, a 0, a 7, and a negative 7. So we can make this a 1 and a negative 1. What else should we do? Let's subtract 3 row 1s from row 2. Subtracting 3, so we're adding 6 here. This becomes an 8. We are subtracting 9, so negative 8. Oh, come on. Pencil's acting up. And we can, well, let's see, we're subtracting 3, so adding 12, so this becomes 16 here. So this is 1, 1, negative 1, 2 after we reduce it down. Okay, what now? Let's subtract row 1 from row 4. That gives us 0, 7, minus 3 becomes 3, plus 4 becomes 4. And let's subtract 7 row 2s from row 4. That gives us 0, 0 plus 7 is 10. Minus 14 is negative 10. Oh, there we go. So we can turn this into a 1, negative 1, and set it to 0, 0 using row 3. And we see we have 1, 2, 3 pivot positions. As a result, the nullity of this matrix is its number of columns, which is 5, minus the number of pivots, which is 3. So we get 2 as our nullity. 12. Let A be a 4 by 5 matrix and let B denote the reduced row echelon form of A. Which of the following statements is true? If the columns 1, 3, 5 of B have leading ones, then the columns 1, 3, 5 of A span R4. So the spanning set theorem, which is something I keep referencing without completely being sure if that's actually the correct one to be talking about, but we have some theorem that says that the fewest number of vectors needed to span R to the n is n vectors. So what A has wrong is that 1, 3, and 5 span the column space of A, but the column space of A cannot span all of R4, even though the input space for this matrix is 4-dimensional. A 4 by 5 matrix, let's just draw that out. 4 by 5 will be wider than it is tall. And so yeah, these vectors do sit in R4. They'll each have 4 entries in them, but since we only have three vectors, there's no way that they can span R4, because by definition they'll have 3 pivots and there'll still be a row in all of them that does not have a pivot. So that's no good. What about B? If the number of non-zero rows of B equals 3, then the number of non-zero columns of B equals 3. Okay, let's think about this. The number of non-zero rows. So let's say we have a pivot, a pivot, a pivot, then we have 1 0 row down here. Okay, so if we have a zero row, then the number of non-zero columns equals 3. Well, in this case, what I've drawn here, that would be untrue. We have 5 total columns. We have the number of non-zero columns equals 3. Yeah, that would be true here. Let's come back to that. I'm still not fully awake. It's 1:51 in the afternoon. C, if B has 3 leading 1s, then the nullity of A is 3. So we know that we kind of have that example already drawn here. If we have 3 leading 1s, then the number of columns, which is 5, is equal to the rank plus the nullity. So our rank is 3, our nullity is 2, and so this is untrue. What about D? If the number of non-zero rows of B equals 2, then one can pick 2 columns of A that form a basis for the column space of A. Yes, yeah, that's true. The two columns that have pivots in them. The number of non-zero. It's all this row stuff that's confusing me. If the number of non-zero rows equals 2, then one can pick 2 columns that form a basis of the column space. Yes, I'm pretty sure that is true there. That's how we find a basis for the column space. Yeah, specifically by picking the columns that have pivots in them. So why is B false? If the number of non-zero rows of B equals 3, then the number of non-zero columns of B also equals 3. Okay, how about this? So we have these pivot positions, and we know we're in reduced echelon form, so we have to have zeros there. But what about after them? Well, we can have 2 free variables, so we could have a 2 and a 4 and a 3, 2 and a 7, 42 there, and there's nothing saying that we can't put those there. And as a result, you'll see we can have three non-zero rows while still having 5 filled non-zero columns. So that is okay. That's why that works. It's a little confusing there. 13. Let A be a 5 by 7 real matrix such that the dimensions of its column space equals 5. Which of the following statements is true? So if we draw out A, we have 5 rows, 7 columns. I'm exaggerating it a little bit, and we know that we have 5 pivots. So the matrix is full rank. It's fitting as many pivots as it possibly can, but we still have 2 free variables, so our nullity is 2. So A is false. The dimension of the null space is 2, not 0. What about B? The columns of A are linearly independent. Nope, because not every column has a pivot. What about C? The rows of A are linearly independent. Well, yes. Yep, I agree with that, because we have a pivot in every row. Yeah, so that should work. What about D? The rank of A transpose is equal to 7. No, the rank of A is equal to the rank of A transpose, and so the rank of A transpose is also equal to 5. And yeah, what follows from that just helps reinforce C, which is the fact that the number of linearly independent rows is equal to the number of linearly independent columns. We know that we have 5 linearly independent columns, thus we should definitely have 5 linearly independent rows. Since we only have 5 rows, that means that the set of rows of A is linearly independent. And then what about E? The dimension of the row space of A is equal to 2. Well, the dimension of the row space of A is equal to the rank of A transpose. The dimension of the rank of A transpose is just equal to the rank of A, which is 5. So no. What about 11? We have some matrix A with 5 columns made out of 4 by 1 vectors. Assume that V3 is a linear combination of V1 and V2, and that V4 is a linear combination of V1 and V2. What can we say about the rank and nullity of A? So because we have at least 2 of these columns that are linear combinations of other columns, so let's see, V3 can be made out of V1 and V2, and so can V4. We're not sure, we don't know anything about V5, but it's fair to say that we can treat V3 and V4 as columns that do not have a pivot in them. So at max, V5 is linearly independent, and so we have three linearly independent columns. Thus, we'll have 3 pivot positions. So I agree with this kind of thing, that rank of A is less than or equal to 3. So that, yeah, well, actually, that's just 4 by 5. Yeah, so this should be our answer here with nullity of A greater than or equal to 2. Because we don't know anything about V1, V2, and V5, how they relate to the other matrices. So it could be that both V1 and V2 are linear combinations of or linear multiples of V5, and that V5 can be formed from V3 and V4. So everything could be dependent on everything else, and thus our nullity would be 5. But yeah, at most our rank should be 3. You could kind of think about this in an extreme case. Let's say we had the 4 by 5 matrix with all zeros the whole way through. These 2 equations would hold, and we couldn't say that our matrix has a rank at all, because everything is a linear combination of everything else. We just can't tell that from the equations that they give. But what we do know is that there are at least 2 free variables. So A is our answer. 8. Let A be an m by n matrix. Which of the following statements is necessarily true? Okay, just look for the rank of A is the same as the rank of A transpose. It will be there, and you won't have to take some time and look through and try to figure out, well, do the columns of A form a basis for the column space of A? Does that always work? No. Just look for A. Rank of A is the same as the rank of A transpose. They really like that one. 13. Consider the equation AX equals 0, where A is a 5 by 7. They also like 5 by 7. 5 by 7 matrix. Which of the following statements is or are true? So AX equals 0 will have infinitely many solutions if our null space has a dimension greater than 0. So the maximum rank that our matrix can have is 5. So 1, 1, 1, 1, 1. See how we can't fit any more pivot positions. There aren't any more rows to go down. So we know that our rank plus our nullity is equal to the number of rows, which is 7. Sorry, the number of columns, which is 7. Our rank is at max 5. And if our rank is 5, then the nullity is 2. But because rank can never be greater than 5, nullity can never be less than 2. So that's some good stuff to know, which means that AX equals 0 will always have infinitely many solutions. What about 2? The matrix A has a rank of less than or equal to 5. Yep, I agree. We could have 0 pivot positions, but as we saw, we can't fit a 6th pivot in anywhere. So this is true. And what about 3? The associated linear system has exactly 2 free variables. Nope, I disagree. What if everything is just 0? We have zeros everywhere. Then we have 7 free variables. No need for our system to always have a rank of 5. So no, this is not true, so 1 and 2 should be correct. And finally, let A be an m by n matrix and B be a non-zero vector in Rm. Which of the following statements is true? Okay. So something important to note for one is that the null space is a subspace of R to the n. So it's a subspace of the number of columns, and we are dealing with a vector in Rm. So what does one say? If Ax equals 0 has only the trivial solution, then Ax equals B has no solution. So let's just make sure that the matrix math works out on this. So if we have A, which is m by n, and we have x, which is n by 1, then yeah, we should get a B, which is m by 1. Yeah, but the subspace itself is a subspace of all the sets of x's. Thus, yeah, it is n-dimensional. Okay, so that doesn't really actually come into play at all. Okay, so if Ax equals 0 has only the trivial solution, what does that mean? That means that our matrix is full rank, and thus that the columns of our matrix are linearly independent, so the transformation represented by that matrix is onto, but it is not necessarily 1-to-1. It will only be 1-to-1 if our matrix is square. So Ax equals B will have some solutions. Let's take a look at the example that keeps being relevant for these ones. Right here we have a, oh sorry, I that one doesn't actually work. So here our rank is 3, the number of columns we have is 3, so the dimension of our null space is 0, thus Ax equals 0 has only the trivial solution x equals 0. Then does Ax equals B have no solution? Well, no, because this matrix right here, what does it do? Well, it takes in R3 and it does literally nothing to it. And so Ax equals B will have a unique solution, not that it needs to be unique for this question, but it will have a solution for all B in R3. So nope, this is not true. What about 2? If Ax equals B has exactly one solution, then A is an m by n matrix with m greater than or equal to n. Okay, let's think about this. So if m is greater than or equal to n, then we have a matrix that is taller than it is wide, and then at max we have a square matrix, m equals n, m equals n. We know that a square matrix, okay, sorry, if Ax equals B has exactly one solution, then A is an m by n matrix with m greater than or equal to n. This should be true, because in order to have exactly one solution, our transformation matrix A has to be 1 to 1-to-1, and the only way for us to have a 1-to-1 matrix is if, sorry, I know what to say, but I'm completely blanking. Sorry, there we go. A 1-to-1 transformation happens if and only if the columns of our matrix are linearly independent. No, oh, I'm clicking the page up button. That's why. Okay, so our columns need to be linearly independent. When can that happen? Well, it definitely can't happen if we have more columns than the dimension of our output space. So we know that at max, so here, let's say that n is 3, m is 4. We could have 1 0 0 0 0 1 0 0 0 0 1 0, and if m is equal to n, let's say that's 3, we have 1 0 0 0 1 0 0 0 1. But the minute we try to add a fourth column, where are we going to put another pivot position? There's no way to put a pivot anywhere where it won't be interfering or already in the span of the other 3. So yes, in order for the columns to be independent such that ax equals b will have exactly one solution, yes, our matrix needs to be either taller than it is wide or square. So yes, that's very long-winded and probably not too helpful, but we got there in the end. Okay, 3. If ax equals 0 has infinitely many solutions, then ax equals b has infinitely many solutions. Yeah, nope, not really. So let's look at this matrix right here. We remember that this is just a matrix that takes in all of R3 and outputs R3, but with all of our z values, so vectors with a non-zero z value compressed onto the xy plane. So if you choose a b vector, if you choose a b vector in the xy plane, you will get infinitely many solutions. But if you choose a vector that is not in the xy plane as your b, you will get 0 solutions. So this is false. And I'd just like to show you. So this ax equals 0 for this does have infinitely many solutions because, we have a null space with a dimension of 1 because we have one free variable. Okay, finally 4. If A is an n by n square matrix, then ax equals 0 has exactly one solution. Well, an n by n square matrix is a condition that we would need to have a transformation that is 1-to-1, but it is not sufficient. So here we have, yet again, this same matrix coming in handy. This is an n by n square matrix, but ax equals 0 has infinitely many solutions because we have a free variable. Here is an n by n matrix with a null space with a dimension of 3. This takes in all of our 3 and just outputs it to the origin. So yeah, no, this is not true. So 2 only is our answer, and we are done. So you can kind of see how the only thing you really need to know that you need to be able to solve all of these questions is the spanning set theorem and the rank nullity theorem, and that's really it.